We are now in the 27th lecture of this course, and we are focusing on the modeling of the automatic voltage regulator. Just to view things in perspective, we have modeled two kinds of power apparatus in this course. One is the synchronous machine itself, and also the excitation system which feeds the field voltage to the synchronous machine. Both of these are power apparatus. The dynamical system is also contributed by the excitation system controllers, and the primary function of the excitation system controllers, which are in fact feedback control systems which are made by us, is to regulate the voltage at the terminal of a synchronous machine. Okay. We saw that if you look at the block diagram of a excitation system controller, we also saw that we can implement other functions like improving the stability of the electromechanical system. This is something we have not shown yet, but in general an excitation system can also provide for this function, and also it can change the field voltage if certain limits are hit. For example, if the field current limit is hit, or later on we will see that if the load angle becomes larger, okay, or delta becomes larger of the machine, then also you can actually change the field voltage and try to rectify the situation. So, in today's class what we will do is consider certain further transfer function blocks. We were discussing transfer function blocks which essentially make up the automatic voltage regulation system in a synchronous generator excitation system. The transfer function blocks we have considered so far are the simple first order transfer function and also a washout circuit. Both these blocks are very essential and important in the discussion of any practical control system. Remember that we are talking of transfer function block diagrams because you will find that most of the representation of control systems will be in this form. So, if you open the manual of a synchronous machine in real life, you will find that the nature of the AVR etc. is expressed not in terms of state space equations or differential equations, but in terms of block diagrams. So, we have to interpret the state space relationships or the mathematical functions in terms of what is given to you in a block diagram. Okay. So, today we will continue that. So, today's lecture is a continuation of our discussion of the automatic voltage regulation. We are really looking at a few transfer function blocks. So, the first transfer function block which we will discuss pertains to the regulator. Okay. In fact, what we did was in the previous class was in fact a first order transfer function block whose block diagram is represented by the figure given at the bottom, and the transfer function represent or rather the state space representation of this is given by this. Okay. So, if somebody gives you 1 upon 1 plus st, you should write it down immediately like this. There is no unique state space representation of a transfer function. Also, if you are given a transfer function like this, okay, it also means it is a linear system, it is a linear time invariant system. Okay. You can actually add some complexities to the transfer function block diagram which make it linear, for example, non-linear. For example, we could have limiters etc., which we will discuss shortly. The second transfer function which we discussed last time was in fact a washout circuit. This is in fact a system which is represented by the block diagram which is given below. The block diagram is kind of expanded, but remember it really the block diagram is a manifestation of the state space equations which are given here on this on the sheet. You will find that there is a minor difference between the block diagram given previously and the block diagram given here in terms of its complexity, but the functions can be in some sense opposite of each other, whereas the first order transfer function block here has got a characteristics of a low pass filter. The washout block here has got the characteristics of a high pass filter in the sense that it has got a unity gain for high frequency and a zero gain for low frequencies. Okay. So, it is essentially used in situations where you want to pass through transients, but you want to block any offset or steady state input. Okay. Now, the state space representation of this block diagram is as given on this sheet here. So, you can have a look at that. we derived it in the previous lecture. Again, there is no unique representation, state space representation of this, but this is the most common representation you will find. Okay. The step response of this transfer function is like this. In steady state, if you give a step here, in steady state you will get 0 here eventually. Okay. Whereas the transient gain is 1. So, as soon as this step occurs, this also responds. Okay. So, in this sense, this particular transfer function is different from the previous one. Of course, these are transfer functions you will encounter, but as I mentioned some time back, the regulator transfer function is usually slightly different. It does contain these blocks sometimes, but the main regulator function of course is to drive the error between the set value and the actual value to 0. Okay. So, what are the regulator transfer functions we shall see shortly, but before we do that we will just look at one more transfer function which is very important, and that is 1 plus ST1 upon 1 plus ST2. Okay. Now, this is another transfer function which you can which you will encounter very often in practice. In fact, if T1 is greater than T2, the numerator time constant is greater than the denominator time constant, then it is known as a phase lead compensator. You will find that if you give a input u which is a sinusoid, then in steady state y which is also a sinusoid will lead the input u. That is if T1 is greater than T2. Okay. So, the block diagrammatic representation is of course given below here. So, this particular compensator, it could be a lead or a lag compensator depending on the relative values of T1 and T2, is a transfer function which is encountered quite often in practice. Okay. Now, if you look at how we got this particular block diagram, you will just see that the transfer function y of s by u of s is basically 1 upon 1 plus ST1 upon 1 plus ST2. You can represent this as K1 okay, plus K2 upon 1 plus ST2, and you can easily verify that K1 is nothing but T1 by T2 and K2 is nothing but T1 minus T2 by T2. Okay. This is the first order block which we have seen already. Okay. So, that is why we get this transfer function which or rather the block diagrammatic representation in terms of the integrator as shown in this figure. Okay. Now, a thing about the steady state response of this to a step change. If you give a step change to this transfer function 1 plus ST1 upon 1 plus ST2, what you will get at the output is depending, suppose if T1 is greater than T2, okay, what is the steady state gain of this transfer function? Well, it is very apparent that this transfer function has got a steady state gain of 1. You just put s is equal to 0 here, you will get what is known as the steady state gain for a step input. So, if you have got a step unit step, in that case your steady state value is equal to the output input. So, the steady state value will be 1. Okay. So, this is the steady state value, this time and this is y. Now, the transient value, if T1 is greater than T2, you will see that for high frequencies which also define the transient gain, okay, you will find that if you put s is equal to j omega and make j omega tend to infinity, you will find that the gain of this is T1 by T2, okay, which is greater than 1. So, what you can expect is if you give a step input, if I give a step input, the output will be like this. So, this is 1, this is T1 by T2. Okay. On the other hand, in case T1 is less than T2, your output will be like this. This is T1 by T2. Okay. So, in this case it is called a lag compensator. Okay. Why it is a lag compensator and why it is a lag compensator when T1 is less than T2 is something which you can easily try to find out by looking at the frequency response of this. This I leave it to you. Okay. Now, the state space representation of this is quite easy to find out. In fact, if you look at the block diagram which is given on your screen, it is quite easy to derive this. So, what comes before the integrator is your state, okay, the derivative of the state. So, you can write this as dx by dt is equal to minus 1 by t 2 x minus 1 by t 2 into u. So, this is actually the state space, the differential equation. The output is t 1 minus t 2 by t 2 into x, this is minus of it, and this is t 1 by t 2 into u. Okay. So, this is what you get as a state space representation. Okay. So, just remember that for every transfer function representation you can get a state space representation. A state space representation is in some sense more rich, in the sense that it tells you the underlying differential equations. It also tells you, because looking at the eigenvalues you can even tell the time response, okay, what the time response is going to be. Of course, using the transfer function representation itself in the Laplace domain, okay, you can also get the time response depending on the Laplace transform of the input. Okay. But working with the state space equations and differential equations is more convenient later on when we will be doing numerical integration as well as linearized analysis, eigen analysis of the system. It is better to write everything in the state space form. Okay. But typically what you will be given in most of your manuals and worksheets of your synchronous generator excitation system, you will find that it is usually the block diagrams will be in this form, okay, using transfer function blocks. Okay. Now, the reason why I have discussed these three important transfer functions, in fact, we have not yet come to the main thing, that is the regulator transfer function. Usually, most of our controllers, including regulators, stabilizers, limiters, will be made out of transfer functions of this kind. Okay. The first one is a simple first order transfer function. It is basically a low pass filter kind of characteristic. Washout circuits which allow transients through, but do not allow the steady state to go through, because it has got a low gain for low frequencies. This lead lag block, on the other hand, is something which you can, by choosing the appropriate values of t 1 and t 2, get the frequency response of your choice. Okay. Of course, you have only 2 degrees of freedom, that is t 1 and t 2 here. Okay. Some of the obvious blocks which you will which I have not discussed explicitly are the gain block. You just have a gain, a summer, a multiplier. A multiplier is a nonlinear block. Okay. So, it can't be really you can't form an integrated transfer function in case you have got multiplier blocks anywhere. Okay. Here you do not have multiplier blocks in the 3 transfer functions which I have the block diagrams which I have shown you here. They have got only summers, gains and integrators. Okay. But you could have, under certain circumstances, limiters and multipliers coming into the block diagram which make your system non-linear. Okay. So, the linear part of the system is usually shown with the block diagrams, the transfer function block diagrams, and I hope you have got now an idea about what kind of differential equations they represent, and in some special cases you know how they behave as well, the 3 special transfer functions which I have described to you. The regulator itself will be made out of some of these blocks, but the typical structure of a plane regulator, it could be containing some of the blocks which I have mentioned some time back, but a plane regulator, a plane PI regulator or a proportional integrator regulator has got this kind of transfer function or this kind of representation. Okay. So, this is a PI regulator block diagram in which this is the simplest possible regulator, in which, in fact, I would not call this the simplest regulator, you can have just a proportional regulator as well. The PI regulator here shown here obtains the error between the set point and the measured value, multiplies it with or gives it a gain of Kp. This is by mistake it has been written as Ki, usually the representation in Kp. Kp is a proportional gain. Okay. You also multiply it by an integral gain Ki and then integrate it. Okay. Then sum the output of the integrator as well as the proportional gain and get your output y. So, the transfer function representation of a PI controller is, the simplest possible PI controller is this. In fact, you can have what are known as PID derivative controllers as well by adding a derivative block. This is uref. Okay. So, this is a PI controller. You can also have a PID controller, which in principle is something like this, plus Kd into S. Okay. This is a derivative. Okay. S denotes a derivative. So, this is again the summing junction, which sums the reference value and the actual measured value. Okay. Of course, if you look at these these components of your block, transfer function block, there is one point which I must make at this point, is that usually it is not possible using a causal or a physically realizable system to make a derivative. Okay. You can chew on this, on what I have just said. You cannot physically realize a derivative function, okay, using causal systems. Okay. So, in such a case, a derivative is actually an approximately realized by using a transfer function of this kind with t very small. So, if you are having transients which are much slower than this t, then this behaves almost like a derivative. Okay. Similarly, a plane gain without any dynamics is often not used. Usually, if you have a plane gain, just a gain here, okay, any noise or distortions in the measured value will get amplified by this gain k. Okay. So, usually instead of just a proportional gain, you will have a proportional gain with a low pass filter kind of first order transfer function. Okay. So, this is what a PID controller is. This is a PID, this is a practical PID controller. Okay. Now, I am not really told you why this is a regulator transfer function. The reason is simply that you take out the difference between the set point and the actual value and you try to amplify it, okay, and change the output. So, why is it a regulator? Because if you have, for example, in an excitation system, you have got the voltage regulator, the set point is given by you, it compares it with the actual voltage. Suppose you have got a PI controller, which I said. So, this error is amplified, it is also amplified and integrated in case there is an integral controller, and given the output of this is the control signal, which is fed to the controlled controlled rectifier of a excitation power apparatus. That in turn changes the field voltage of the synchronous machine. The synchronous machine field voltage changes the terminal voltage of the machine. So, this is EFD and this is your control signal, we will call it VC. This is how the system works. So, if you have got an amplifier, it tries to change this till this error goes down to 0. Okay. Now, of course, there is a catch here. Should error here become 0 in steady state if you use a PI controller? The answer is yes. If you look at the block diagram which is given on your screen, note that you have got an integrator at the bottom here. Okay. This is the integrator. Now, if you have got an integrator, what is the job of an integrator? Well, it integrates. Okay. So, it integrates whatever appears at its input here, okay, which is just after the integral gain. So, the thing is that if you want to reach steady state, you should stop integrating. Now, what does that mean? If you are in steady state, it means that all the variables reach a steady value. Now, if an integrator has got an input which is non-zero, there is no way you will be in steady state, because the integrator keeps on integrating whatever is there in the input. So, if you are using a PI regulator, in that case the input to the integrator has to become 0. The input to the integrator is nothing but Ki into the error, that is U ref minus U measured. Okay. So, it follows that in case you are in steady state and you are using a PI regulator, then the steady state error is 0. So, you can say that if your system is working well, it is stable. That is of course not something which I have proved. The point is that if you have designed your system well, your feedback control system well, it is stable. Then in steady state, if you are using a PI controller, a controller which has got an integral component as shown there, in that case the steady state error is driven to 0. Is that okay? So, just to do a quick example, suppose I have got a PI controller, say this has got a gain of 100, this is a proportional controller, this is the integral controller. Suppose this gain is 500 and this is added here. You have got an integrator here of the PI controller. So, this is your I channel, the P channel, this is your input, this is U, this is U ref, this is U measured. Suppose the system which you are trying to, this is just an arbitrary system. Okay. Suppose I have got a system of this kind. This is a PI controller which is trying to get the output y equal to U ref. Okay. So, this y has to become equal, we want it to become equal to U ref. Okay. So, if you have got a system like this, okay, you will find that in steady state this error which appears here, this is the error, has been driven to 0. Okay, in steady state. Okay. So, in fact, if U ref is a step input from 0 to 1, in steady state this error has to be 0. So, this will be 0. If this has to be 0 and this is a feedback system of this kind, y also has to be 1. Okay, y has to be 1. If y has to be 1, can you tell me what is the steady state value out here? Well, it is going to be 1. Remember that the steady state gain of the transfer function 1 upon 1 plus st is 1. Okay. So, if this is 1, what is the value here? See, this is 0, the error is 0. If you just multiply anything with 0, of course, it is going to be 0 here. So, and this is 1. So, the output of the integrator is 1. The output of the integrator is 1, does it mean that the input has to have a certain value? Well, no. This is the value which the integrator has integrated up to. Okay. The input to the integrator in steady state has to be 0, otherwise the integrator will integrate whatever input comes and change this value. Okay. So, this is the steady state values in case you have got step change given to the system of this kind, which has got a PI regulator and the thing to be controlled has got a transfer function upon 1 plus st. Okay. In our case, you will have to replace this 1 upon 1 plus st by the dynamical system corresponding to the excitation power apparatus and the synchronous generator. The y is nothing but the terminal voltage. Okay. So, this plant is very simple. In our system, the plant which we are trying to control will consist of the excitation system apparatus as well as the synchronous generator. Okay. So, this is just a toy example. In actual practice, for our systems, you will have a complicated plant which has to be controlled. Okay. So, a regulator is, you can say, trying to control a plant. Okay. Now, so a regulator, if you look at it, consists typically of a proportional controller or a proportional integral controller or a proportional integral derivative controller. Okay. If you have got a proportional controller, for example, something simple like this. Okay. Simply again, and here is the output. This is a proportional controller. Okay. So, this is U ref and U. Remember, a regulator is defined as something which is trying to get a measured value equal to the set point value. Okay. So, this is all a regulator. Now, this is a proportional controller. Now, a proportional controller, to have any non-zero output, it has to have a non-zero input. So, it follows that if you are using a proportional controller, in that case steady state error between the set point and the thing you want to follow the set point is not 0, not equal to 0. Why? Because in case you want to have this to have any control signal which is going to affect your excitation apparatus, then this has to be non-zero. Okay. Now, if this gain is very large, then to get a certain control signal in order to obtain the voltage you desire or near the voltage you desire, in that case the error need not be too large. So, if I use a larger gain in a proportional controller, then the steady state error is going to be lower, because to get the same value of the excitation required to get a certain value of u, you require a smaller value of error. Okay. So, in a proportional controller, steady state error is not equal to 0, but a high gain proportional controller will have lower corresponding steady state error. Okay. Now, as in any control system design, it is not guaranteed that your system is going to be stable for any kind of gain. Okay. So, you actually have to do a control system design in order to ensure that your system is stable under various situations. In fact, we have I am sure you have done a course on control system design sometime in your previous in the previous years. Now, this particular system which I showed you, which is shown here on the sheet, is in fact you can show that it is going to be stable. Okay. If t is not greater than 0, then you can show that this particular system is stable, a unity feedback system is stable for any value of p and I. Okay. So, we can have a system of this kind which is stable. Okay. You can just verify this, okay, that at least if I got just a proportional controller, it is easy to show that this system is always stable. Okay. So, this is something you can just check out. Okay. Is it stable with just a proportional controller? Is it stable with a proportional integral controller, and what are the gains for which it is going to be stable in terms of this this time constant t. Okay. So, this is a separate subject of control system design, which is related to power system dynamics. If you are going to do power system dynamics, you should know a bit about a little bit at least about control system design and stability. Remember that just using a proportional controller or a proportional integral controller is sometimes not adequate. Okay. That in that context, you may actually have to use the transfer functions which I have discussed before. For example, instead of a plain proportional integral controller, you may not get a stable performance. Okay. So, you may have to add a lead block or a lag block in order to improve the performance of the P or PI controller which you will use. Okay. So, this is one thing which you may see in a a control system, that in addition to the proportional or proportional integral controller, you also have these blocks which try to improve the response. What do I mean by improved response? Well, one of the things you should ensure with your regulator is that if, for example, I give a step change, this is one way to specify the performance of a regulator. If I give a step change, how much time does U require to settle down? Okay. So, U is actually determined by a fairly complex processes. Remember that for a AVR, the output of this is the control signal to the excitation apparatus. The excitation apparatus itself may have very significant dynamics, as we see in a brushless excitation system. Then that determines the field voltage. The field voltage, again, field voltage change results in a terminal voltage change of the synchronous generator. It is a fairly complicated way, because you will have to actually solve all the differential equations either numerically, or if we linearize it around an operating point, you can even do a linearized kind of analysis. what I want to say is that eventually the U, the in a automatic voltage regulator is going to be determined by a fairly complicated set of dynamical processes. Okay. So, eventually a response is going to be something like this, it could be something like this. So, for a step change, if you look at this, for a step change in the input, you could have, for example, so if this is your voltage reference, your actual V could be like this. Now, obviously, you should design your system so that it settles fast. If a system settles down fast, it also means that the modes which are observable in the voltage are more stable, they are more having real parts which are more on the left hand side of the complex plane, and as a result of which they decay very fast. Okay. You also would like your rise time, okay, to be fast, you do not want it to rise like this. Okay. The best possible response could be something like this, you want it to rise and settle down immediately. Okay. So, that kind of response you could want. In the case of a excitation system, remember that the conditions of the synchronous generator, whether it is open circuited on no load or it is at half load or at full load, will really change the kind of response you will get. The plant of the system, which is the exciter power apparatus as well as the synchronous generator and the power system to which it is connected, will really determine the response. So, what you need to do when you are trying to design a system is to use not only proportional integral controllers, but you may require to use a lead or a lag block in series with the proportional controllers in order to get some degrees of freedom. The degrees of freedom are in fact the time constants T A and T B of the lead or lag compensator. You get these degrees of freedom in order to improve the response. Okay. So, this is what is very important, which you should note. So, if you look at a typical regulator, it is not just consisting of proportional controllers. Typically, you will find that it is consisting of Vref, V, a lead or a lag block, usually depending on the situation you could use, most likely you will use a lag block if you want to achieve some functionality. And a PI controller, often you will find it is just a high gain proportional controller, integral component is absent in many kinds of AVRs. Okay. So, this is what you will normally see. You may sometimes, I will just redraw this, what you will normally see is, this is the summing junction of course, then you have got a lead or a lag block, you could have a cascade of these, you could have another for example, if you require it, if your time response has to be further tuned. Then you have got a PI controller, but usually a high gain P controller suffices. Okay. So, it has the system will have a steady state error here, but if it is a high enough gain, the steady state error will be negligible. Okay. So, this is usually what your AVR is going to look like. This is the control system. Now, sometimes it may not be adequate to get a very good response just with these blocks. Okay. So, in some AVRs, what you will find is that the excitation system is connected to this, of course, the synchronous generator. The field current is taken as a feedback. The field current is taken as a feedback, and you have got this additional block. Of this kind, which is fed into this summing junction here. Okay. So, you may have another block like this, which takes a feedback of the field current, okay, of the synchronous machine. In a brushless excitation system, we may not be able to get the field current of the main generator, but you may be able to get it of the excitation system alternator. So, in some cases you may take input from this point. Okay. Now, this may be an extra block which may be present in certain excitation systems, certain AVRs, to improve the the stability of this control system. Okay. So, this is often called an excitation system stabilizer. Remember, it has got a transfer function which is SKF upon 1 plus STF. So, this is essentially like a washout block, okay, with a slightly different gain, of course. The steady state gain of this would be Kf. Okay. So, this the transient gain would be Kf and the steady state gain is 0. Okay. Now, one of the things you should remember, though this excitation system stabilizer is being fed into this summing junction, its output in steady state is going to be 0. So, the output in steady state is going to be 0. So, it will not interfere with the regulation function out here. Okay. So, in steady state this will be 0. So, V will try to be driven to be Vref, okay, by this controller. Okay. So, this does not contribute anything at the summing junction. If something non-zero is contributed at the summing junction, then the regulation function will get compromised. Okay. But this is not the case, because in steady state the output of this is 0. So, you may find, we will not actually go into the design of the AVR itself, but you may find blocks like this in addition to the regulator, the basic regulator, which is a proportional controller. Okay. So, this is what our controllers typically look like. There is another block which I need to discuss at this point. We have already kind of got a flavor of that block before, that is the limiter. Now, we have without much spending too much time, if you recall, this was the kind of symbolic representation of a limiter which was given. So, if you have got an input u, it will get clipped to the values specified here. So, if I specify this value as +1 and -1, in that case this input, suppose you have got an output y dash, y will not be equal to y dash if y dash exceeds these limits, it will just get clipped at that limit. This is often called what is known as a soft limiter. In fact, we have used the limiter to model the converter, static converter, which is used in the excitation power apparatus. Okay. Now, this is simply a clipper, okay. It simply clips the output. So, if you find you have got something like this, this is simply clipping the output which appears here. But remember, it does not affect the output y dash. Okay. So, it allows y dash to get any value you want, but it clips the value of y dash in order to get y. Okay. So, this is a soft limiter. Okay. You can have another class of limiters which is called a hard limiter. In order to do that, let us take the example of a simple integrator. Suppose I have got an integrator. And I try to limit it. Okay. This is a soft limit. Okay. So, if I got an input u, it will be integrated in order to get y dash. Y will be the clipped value of y dash. Of course, if y dash does not exceed any of the limits specified here, okay. For example, +1 or -1, this is an example of a limit. In that case, y dash is equal to y. So, only when the limit is exceeded that these limiters come into play. Okay. A limiter makes the system non-linear. Okay. So, although our transfer function representations etc., are actually of linear time invariant systems, when you have limiters included in the transfer function blocks, effectively a system becomes non-linear. Okay. So, let us now look at another kind of limiter. It is represented in this fashion. The difference between these two limiters, this limiter and this limiter, is that in case the output y exceeds the limit or tends to exceed the limit, the integrator stops integrating. So, just try to chew on this statement. The integrator stops integrating in case the limits are exceeded. Here, the integrator does not stop integrating, it keeps integrating, the output simply gets clipped. Okay. So, y dash and y need not be equal and the output gets clipped. Here, if y dash exceeds the limit specified here, say +1 and -1, say this could be anything. In that case, the integrator simply stops limiting. In some sense, you can say that it starts integrating 0 instead of u. Okay. It starts integrating again when there is a chance that the limit the output y can come out of its limit. So, if you, for example, if the output is at +1, which is the limit specified here, then this integrator stops integrating till u starts becoming negative and there is a chance for this y to come out, okay, or start coming out of the limit. You can take, say, an example of a simple system like this. Okay. So, if I have got an integrator and I am trying to integrate input u, say u is cos omega t. Okay. So, let us assume that this integration has been going on for a while. I will just show it this way. Suppose u is cos omega t. Okay. Then of course, the output y would be, so if we have got input as omega into cos omega t, okay, and you try to integrate it, you will get sin omega t. Okay. So, omega into cos omega t, suppose is this, you will eventually get sin omega t is something like this. Yeah. So, this is your sin omega t, this is your output y. Okay. Now, suppose I have got a soft limit, okay, which is put at plus 0.5 and minus 0.5. In that case, the output would be clipped. So, what you will get in fact at y is not this, something which is clipped at 0.5, plus 0.5 and minus 0.5. So, this is the response of a soft limiter. Okay. So, it just clips the output. So, what you will get at the output is what is in black, that is this. I will just darken it a bit so that you can see it. So, what you see is the integrator does integrate, okay, as per its rule. So, the red curve is what you get simply by integrating omega cos omega t. Okay. But what you get at the output is a clipped version of this. Okay. The integration operation itself is not affected. Now, if you on the other hand try to integrate by using in the presence of a hard limiter, so you have okay, it is not very much well drawn, but anyway. So, this is cos. So, if you look at how this particular system behaves, you will see that it integrates up to 0.5. This is actually will not meet at 0.5, but anyway, it will integrate up to 0.5. Okay. After that, it gets limited. Now, it will go on staying at the limit. Okay. So, what happens is that the integrator itself stops integrating. It is not that the integration is going on. At this point, we do not continue with the integration. We stop the integration and the output remains at this value. This is exactly as we got before, but whenever the integrand, this is u, the input becomes negative, there is a chance of coming out of its limit, okay? Because if you integrate a negative quantity, then you start decreasing from where you are. So, what will happen is you will come out of the limit right away. Okay. So, this is what happens in case you have got a hard limit. In fact, if you have got a soft limit, it is this, and a hard limit, it is this. So, whenever you have got an integrator which is hard limited, you will find that it stops integrating as soon as the head limit is hit. In fact, this is desirable under certain circumstances. In this earlier circumstance with a soft limit, what happens is the integrator goes on integrating and you may really go on, although your output is being clipped, the integration here is continuing and you may find it is taking much longer time to come out of its limit, even though the input u has got become negative, okay, in this case. So, the input u has become negative at this point, but it comes out of the limit only at this point, whereas here with the hard limiter at this instance itself the integration resumes, because there is a tendency to reduce the value because u has become negative. Okay. So, this is what is known as a limiter. So, you will find that most control systems will be designed with limiters in order to prevent. See, what happens if your limit has been reached? You do not want to go on making the controller trying to do something, anyway it is not getting implemented. Okay. So, it is a good idea to put limiters wherever feasible and wherever it is reasonable to do so. So, you will find typically have a limiter here on the hard limiter on the integrator and a soft limiter here which will clip the output as well. Okay. Of course, if you are just an integral controller which is hard limited, you do not have to put a soft limiter again. Okay. But here since you have a combination of P and I, you can have a hard limiter as well as a soft limiter. So, on the whole you will prevent the values from going out of range. Okay. So, this is what typically you will find in your AVR controllers. Now, suppose we want to take up now a simulation of automatic voltage regulator. We have actually discussed the way control systems are, okay, typical control systems associated with the regulator are. We have of course not discussed about limiters, etc. Right now we will focus on the regulator itself, regulating function itself. Remember that Vref of the synchronous of this AVR can be modified by limiters and stabilizing functions, okay, whenever there is a need to do so. Okay. So, for example, if the synchronous machine field current is exceeded, you may wish to sacrifice the regulation function, but reduce the field voltage, so as to reduce the field current. Okay. So, if some equipment limit is being hit, then the limiter may wish to reduce the field voltage instead of carrying on with the regulation function. So, in some sense the Vref objective, the objective of making V as close to Vref as possible is compromised, and you would rather maintain limits. Okay. We saw that if you want to improve the dynamics of one or more modes of the system, you may actually put in stabilizing functions. One of the functions we saw was an excitation system stabilizer, but the main characteristic of a stabilizer is that its output in steady state is 0. Okay. Now, we will move on to trying to simulate an automatic voltage regulation system along with AVR. So, if you really look at what is involved, you have got the mathematical functions or the state space representation which describe how an AVR works. Okay. So, AVR of course will require you to have a set point which is given. Okay. It takes the feedback of voltage, okay, the terminal voltage of a generator. The excitation system gives the control signal to the excitation power apparatus, that gives the field voltage to the synchronous machine. The synchronous machine output is of course what you measure using a potential transformer, which is fed to the AVR. Remember, the AVR is not a power apparatus, it is a control system. Okay. The AVR itself may take feedback signals like the field current. Okay. So, this is a typical structure of the system. What we will do in the next class is try to analyze a system of this kind. So, the simplest thing we can do is, suppose we take a static excitation system. So, if you have got a static exciter as shown in the screen on the screen, then the converter model is usually a static one, and the only thing which you need to represent is the field voltage limits, the limits of the converter itself. I am sorry. The limits of the converter are determined by the terminal voltage of the generator itself, because the power apparatus of the excitation system is fed from the terminal voltage of the synchronous machine itself. Okay. So, if you look at this, it is fed from the terminal voltage of the synchronous machine. So, the limits are effectively decided by the terminal voltage of the synchronous machine. Okay. So, the converter itself, we will assume that it is a static model, it is a simple model in the sense that it implements whatever the control system tells it to do subject to the limit. So, if I want, so we will kind of have, let us say, we will just model it this way. This is the terminal voltage of the synchronous machine. These are the limits imposed on the converter output by the terminal voltage of the synchronous machine. This is the field voltage. Okay. Let us assume that this field voltage is in per unit. We have defined the per unit system before. EFD is 1 if it results in an open circuit line to line voltage for a star connected synchronous generator at rated speed. Okay. So, it develops the rated voltage at the rated speed, then we call that voltage as 1 per unit. Okay. So, we will not represent it in volts, but in per unit. Okay. Now, the control signal which gives this EFD, okay, again can be expressed in terms of volts, it is a signal, okay, which is given to this converter. But if I say that 1 per unit of, let us define or normalize our control signal in such a way that 1 per unit here, a control signal of 1 per unit results in 1 per unit EFD, then the gain of the converter becomes 1. So, this is also represented in per unit. Okay. The AVR, this is the excitation apparatus. Okay. The AVR, let us assume, is a simple proportional controller of this kind. This is the error signal, this is Vref, this is V. So, this is what is your AVR and power excitation system block diagram. Okay. Ka is typically, it could be say around 200 to 300 or even 400 per unit by per unit. The gains are in per unit. So, what I will do is I will also do this sum. So, all these gains etcetera are expressed all in per unit. So, I have already described what this per unit system means. Okay. As far as the field voltage, the control signal, the terminal voltage is expressed in per unit on the generator terminal voltage base. Okay. That is the rated kV of the synchronous machine. So, if I represent it this way, then K is typically of this value. Okay. It could be say 200 or 300 or 400. Okay. It is usually kept quite high. So, that to get a value say of EFD 1 here, the amount of steady state error required here is very small. Okay. Remember that now, this TA is usually very small, this is of the order of 1 cycle, that is all, say 20 milliseconds. So, this is the block diagram of excitation system with just the regulator included. We could have included many more possibilities. In fact, in this course we will not do that. We will include a simple excitation system model, okay, using a static exciter, okay, and this we will use to study the voltage regulation of a synchronous machine. What I will do is now incorporate the equations which are embodied in this transfer function or these limiter and summer blocks, write them as state space equations, okay, interface them with the synchronous generator equations, connect a synchronous machine to another voltage source, okay, and try to regulate the terminal voltage of the synchronous machine. We will do one extra thing, we will not connect the synchronous machine directly to a voltage source, we will connect it via a model of a transmission line, a very simple model of a transmission line. Modeling of a transmission line is something we will do in brief later in this course, we will just take a simple model when we are studying this. So, with this we will come to the end of this lecture. In the next lecture, stay on for the incorporation of an AVR into the synchronous machine equations and the simulation of the voltage regulation action.